There is a single word buried inside an official interagency release that has quietly rewritten the boundary between what we assumed was possible and what the data is now forcing the scientific community to confront. Not a paragraph, not a press conference, one word. And the institutions that selected that word, institutions staffed by the most analytically rigorous minds the civilization has produced, chose it with a precision so deliberate, so compressed, so forensically exact, that what it does not say is louder than anything it does. That word is differed.
4 independent instruments, 4 entirely separate positions distributed across hundreds of millions of kilometers of solar system geometry. 4 distinct wavelength regimes, each probing a different layer of chemical and physical reality. And the volatile production rate measurements those 4 instruments returned about a single object, the same event window, the same anomalous visitor accelerating through the inner solar system, differed. Not from each other in the ordinary statistical sense of instrumental variation. Not in the way that calibration margins and signal-to-noise thresholds explain away discrepancy. They differed from every comparable measurement ever extracted from any cometary body across 3 full decades of dedicated observational science. This is not a developing story in the journalistic sense. It is a forensic assembly. It is what happens when you lay out every confirmed data point from the Sphere-X Space Telescope, the James Webb Space Telescope, the MAVEN Mars Atmospheric Orbiter, and the Atacama Large Millimeter Array, operating simultaneously across a single observational window. And you let the compound records speak, without the interference of institutional restraint or the comfort of prior assumption. What you get is not an anomaly in isolation. What you get is a convergent portrait of an object that the natural framework cannot fully reassemble into a coherent picture without leaving structural fractures that the data itself forces open. Welcome to the Forensic Deep Dive. Let us begin where the chemistry does, to understand why the deuterium concentration documented in the volatile output of 3I/Atlas constitutes a formation environment constraint of absolute consequence. You first need to understand what deuterium actually records. Deuterium is the stable, heavy isotope of hydrogen. Its nucleus carries 1 proton and 1 neutron, compared to ordinary hydrogen's single proton, making it approximately twice the atomic mass of its lighter counterpart. In the cold molecular clouds where stellar nurseries and their accompanying protoplanetary systems coalesce from interstellar gas and dust, deuterium enrichment occurs through a precisely defined pathway of ion-molecule chemistry. At low temperatures, this chemistry preferentially incorporates the heavier isotope into hydrogen-bearing molecular bonds, particularly into water ice, because the energy difference between deuterium-bearing and hydrogen-bearing molecular configurations becomes energetically favorable only in extreme cold environments. The colder the formation environment, the more efficiently the chemistry drives deuterium into molecular water structures. What this means in practical astrophysical terms is profound. The deuterium to hydrogen ratio locked inside an icy body's molecular architecture is not decorative. It is a thermometric record, a chemical timestamp of the precise temperature conditions under which that ice crystallized. It is nature's own laboratory notation, written in isotopic ratios, preserved in molecular bonds, and legible to spectroscopic instruments sensitive enough
to read it across interstellar distances.
In our own solar system, the cometary population formed in the cold outer protoplanetary disk at formation temperatures spanning approximately 30 to 150 Kelvin, depending on their radial distance from the protosun during the disk's formative epoch. Their deuterium to hydrogen ratios reflect those conditions. Across 30 years of cometary observation, spanning missions from Giotto to Rosetta to the deep impact flyby of Comet Tempel 1, the measured range sits between approximately 150 and 300 parts per million of total hydrogen content. This is the baseline. This is what solar system chemistry produces. This is the spectroscopic fingerprint of formation in the cold but not extreme outer disk of a second-generation stellar system like our own. The Sphere-X Space Telescope measurement of 3 I/Atlas's water vapor emission returned a deuterium concentration of approximately 1% of all hydrogen atoms in the sampled volatile release. 1 atom of deuterium for every 100 atoms of hydrogen. Theoretical models of isotopic chemistry are absolutely unambiguous about what this number requires. A deuterium concentration at that level does not form in the cold outer disk of a solar system. It does not form in a molecular cloud at ordinary star-forming temperatures. It forms only in environments where ambient temperatures fall below 30 Kelvin, below negative 243 degrees Celsius, temperatures colder than the dark hemisphere of Pluto at its furthest orbital point from the Sun, colder than any thermally isolated environment within the gravitational influence of our star, colder than anything in the catalogued physical inventory of this solar system except the deep interstellar void itself, the lightless corridor between stellar systems where no stellar radiation field penetrates, where molecular chemistry proceeds across timescales measured not in millions, but in billions of years. The measured deuterium ratio in 3 I/Atlas is not slightly above the solar system cometary range. It is 10 times above the upper boundary of that range. 10 times! This is not instrumental artifact. This is not calibration drift. This is a formation environment signature that places the chemical origin of this object's water ice in conditions that do not exist anywhere within the gravitational domain of our Sun. And this finding is in precise alignment with the James Webb Space Telescope's isotopic composition data, which places 3 I/Atlas's origin epoch in the metal-poor early galaxy 10 to 12 billion years ago, at a cosmological moment when the universe itself was less than a quarter of its current age, when the interstellar medium had not yet been seeded with the heavier elements that second and third generation stellar nucleosynthesis would later scatter across the galactic disk. Now, here is where the Kaku lens must be applied. Because deuterium is not merely a formation thermometer, through the framework of energy physics, through the lens of what Type 2 and Type 3 civilizations on the Kardashev scale are theoretically capable of extracting from the fundamental forces of nature, deuterium occupies a very specific position. It is the primary fuel substrate for the most energy-efficient nuclear fusion reaction pathway accessible in the known physical universe. Deuterium-deuterium fusion, the DD reaction, produces helium-3 and a free neutron, releasing energy at a rate that dwarfs every chemical combustion pathway by orders of magnitude. Deuterium-tritium fusion, the DT reaction, produces helium-4 and releases 17.6 mega-electron volts of energy per single reaction event. These are not exotic laboratory curiosities. These are the nuclear processes that ignite and sustain every star in the cosmos. They are the reactions that power the thermonuclear cores of main sequence stellar objects, from red dwarfs to blue supergiants. They are the reactions that experimental fusion programs on Earth, from the ITER tokamak in southern France to the National Ignition Facility in California, have pursued for 7 consecutive decades as the theoretically unlimited energy source that could elevate humanity toward the threshold of a Type 1 civilization on the Kardashev scale. A spacecraft designed for transit across interstellar distances, across the light-year gulfs that separate stellar systems, requires a propulsion energy source of a fundamentally different category than anything the chemical rockets of our current technological epoch can provide. The physics is not ambiguous. The inverse square law of energy dissipation, the relativistic energy requirements for meaningful transit velocities, and the timescale constraints of biological or even machine-mediated navigation all converge on a single conclusion. Interstellar propulsion requires fusion-level energy output at minimum. And if an engineering civilization were selecting a propulsion fuel for a vehicle designed to operate across a 10 billion year mission profile, deuterium fusion would be the optimal substrate. Not because theoretical models prefer it, but because the nuclear binding energy mathematics of the Standard Model leave no more efficient alternative accessible without entering the territory of antimatter annihilation or space-time metric manipulation. The 1% deuterium concentration in 3I/Atlas does not constitute proof of fusion propulsion architecture. The forensic record does not permit that conclusion from a single data point in isolation. What it does constitute is a concentration 10 times above anything that solar system formation chemistry produces, occurring in an object whose every additional chemical characteristic compounds the deviation from the natural baseline in a consistent directional vector. Consider the methanol ratio. This is where the departure from any previously cataloged natural baseline becomes, in the precise quantitative language of millimeter wavelength spectroscopic analysis, the second highest measurement ever recorded for any cometary body in the full history of systematic astronomical observation. The Atacama Large Millimeter Array's radio frequency mapping of 3I/Atlas's coma chemistry documented methanol release at a ratio to hydrogen cyanide between 70 and 120 times higher than the methanol to cyanide ratio measured in any standard cometary body. There is precisely one other object in the entire 30-year observational archive that approached ratio values in that magnitude range. It did not carry the same deuterium enrichment signature. It did not carry the same formation age constraint, and it did not present the same compound multi-parameter anomaly profile that transforms 3I/Atlas's methanol concentration from merely unusual into forensically significant. Methanol, chemical formula CH3OH, 1 carbon atom, 4 hydrogen atoms, 1 oxygen atom in tetrahedral bonding geometry. In the framework of prebiotic chemistry, the chemistry that predates and precedes biological organization, methanol is not a peripheral molecule. It is a foundational intermediate in the reaction cascade pathways that generate amino acids, simple sugars, and the nucleotide base structures of ribonucleic and deoxyribonucleic acids under appropriate conditions of temperature, ultraviolet radiation exposure, and mineral catalytic surface availability. Researchers tracing the molecular ancestry of terrestrial biochemistry backward through atmospheric and aquatic chemistry have consistently identified methanol as a critical upstream intermediate, a molecular precursor whose presence in sufficient concentration
opens downstream reaction pathways toward the assembly of life's fundamental building blocks.
An object releasing methanol at 70 to 120 times the normal cometary ratio is not simply an interesting spectroscopic outlier. It is depositing prebiotic chemical substrate into whatever planetary environment it passes through at a volumetric rate that has no precedent in the natural cometary catalog. And the methanol is not releasing uniformly. The volatile production sequence, documented as 3I/Atlas, progressed through its inner solar system approach trajectory, revealed a highly ordered release architecture. In the early orbital approach phase, the object preferentially emitted carbon monoxide, carbon dioxide, and methanol. Water vapor release was measurably suppressed, delayed, held back beneath a protective outer layer that required months of sustained solar thermal energy input to breach. That outer layer, estimated at approximately 20 meters of thickness based on thermal emission modeling, is composed of radiation-processed molecular material transformed over billions of years of isotropic exposure to galactic cosmic ray flux in the interstellar medium. Galactic cosmic rays are high-energy charged particles, protons, alpha particles, and heavier atomic nuclei, accelerated to relativistic velocities by the expanding shock fronts of supernova blast waves and propagating through the interstellar medium simultaneously in every spatial direction. Over a 10 billion-year interstellar transit, isotropic cosmic ray bombardment transforms the surface and near-surface layers of an icy body through the process of radiolysis, the radiation-induced decomposition of molecular bonds, creating new molecular compounds, restructuring chemical configurations, and progressively hardening the outermost material into an amorphous, carbonaceous crust with substantially enhanced structural integrity compared to the pristine volatile ice beneath. The 20-meter carbonaceous processing crust of 3I/Atlas is consistent with the theoretically expected product of 10 billion years of cosmic ray radiolysis applied to cometary ice composition in the deep interstellar environment. That is a natural explanation for the crust's existence. The forensic question it raises is not why the crust formed. The forensic question is, what did that crust preserve, and for how long? For a 20-meter crust to maintain the interior volatile chemistry of an object across a 10 billion-year transit arc, across the full thermal range from 3 Kelvin in deep interstellar space to the concentrated solar irradiation environment of perihelion passage, while retaining methanol to cyanide ratios 70 to 120 times above any catalog cometary baseline, while preserving deuterium concentrations 10 times above the solar system upper boundary, while carrying carbon and oxygen element abundances that theoretical models show are inconsistent with the confirmed metal pore formation epoch verified by JWST isotopic analysis, that crust was not simply a passive byproduct of radiation exposure. It was executing a preservation function across a timescale that passive geological processes have never been independently documented to sustain in any naturally occurring cometary body of equivalent composition.
This is where the mass anomaly enters the forensic sequence. And when it enters, it does not leave room for comfortable coincidence. The estimated total mass of 3I/Atlas is approximately 1 billion metric tons, contained within a nucleus whose diameter is estimated at 2.6 kilometers. For a reference scale that makes the significance of this number immediately legible, 1I/Oumuamua, the first confirmed interstellar object detected transiting our solar system, announced in 2017 from observations at the Pan-STARRS telescope facility, carried an estimated mass of approximately 10 million kilograms. 3I/Atlas is at minimum 100,000 times more massive than Oumuamua, and it contains that mass within a nucleus that is emphatically not 100,000 times larger in diameter.
The density implied by that mass-to-volume ratio is not consistent with the porous aggregate structure of naturally formed cometary nuclei. Standard cometary nucleus bulk density, established across multiple in situ measurement missions, including the ESA Rosetta spacecraft's extended orbital observation of comet 67P/Churyumov-Gerasimenko, falls between approximately 500 and 600 kilograms per cubic meter. This low density is a diagnostic signature of the highly porous, loosely aggregated ice and silicate dust composition of bodies that accreted from the protoplanetary disk under low gravity, low velocity accretion conditions. Water ice at standard density is approximately 917 kilograms per cubic meter. Silicate rock averages between 2,000 and 3,000 kilograms per cubic meter. A porous mixture of ice and rock in the observed proportions produces exactly the bulk density range measured for natural cometary nuclei. Ice does not produce the density implied by 3I/Atlas's mass-to-volume ratio. Conventional rock does not produce that density at that scale in an object of this diameter. Whatever occupies the interior volume of 3I/Atlas beneath the 20-meter process surface crust, whatever compositional architecture the molecular fingerprint distribution data documents in the spatial structure of the coma material, is denser than any natural cometary composition the observational record has ever documented in an object of this physical scale. The density anomaly does not exist in a data vacuum. It exists in confirmed simultaneous presence with deuterium concentrations 10 times above the solar system upper boundary, methanol to cyanide ratios between 70 and 120 times the natural cometary baseline, carbon and oxygen element abundances contradicting the confirmed metal-poor formation environment established by spectroscopic isotopic analysis, a 20-meter preservation crust that maintained anomalous interior chemistry across 10 billion years of isotropic cosmic ray bombardment, and an anti-tail structure that persisted beyond the viewing geometry window that standard cometary dynamics fully explain. Let us examine the antitail. An antitail is a cometary optical feature in which a portion of the coma material appears to extend toward the Sun rather than away from it in the expected solar wind-driven direction. The standard physical explanation for antitails involves the projection geometry of large dust particles released by the cometary nucleus. These particles, significantly larger and denser than the fine-grained dust that forms the principal tail, lag behind in the orbital plane rather than being efficiently accelerated away by solar radiation pressure. When Earth's viewing angle relative to the comet's orbital plane falls within a specific geometric window, these lagging large particle structures project against the forward direction of orbital motion and create the apparent inward-pointing antitail structure. The critical operational feature of this geometry is that it is temporary. The projection effect disappears as Earth's orbital motion changes the viewing angle. The antitail of 3I/Atlas persisted beyond the temporal window that the Earth viewing geometry alone can explain. It remained visible after the projection conditions that produce a natural antitail had passed. That persistence requires either dust particles of anomalously large size and density remaining gravitationally associated with the orbital plane for substantially longer than standard cometary dust dynamical models predict,
or a structural feature of the coma architecture that is not reducible to a projection artifact. Neither explanation has been formally published. The anomaly entered the observational record. The observational community noted it. The discussion moved on.
Now assemble the complete forensic compound sequence.
Deuterium at 10 times the solar system upper boundary. Methanol at 70 to 120 times the natural cometary ratio. Carbon and oxygen abundances contradicting the confirmed metal-poor early galaxy formation epoch. 1 billion metric tons of mass within a 2.6 kilometer nucleus whose density exceeds any natural cometary compositional model. A 20-meter preservation crust that maintained the anomalous interior chemistry across 10 billion years of interstellar cosmic ray bombardment. An antitail that outlasted the geometric conditions that naturally produce such structures. 4 independent instruments across 4 wavelength regimes confirming in the same observational window that the measurements differed.
The compound probability calculation that the natural hypothesis requires you to simultaneously absorb across all of these confirmed data points is not a number that sits comfortably within any coincidence framework currently operational in planetary science or cometary dynamics. Each individual anomaly carries a proposed natural explanatory pathway. The systemic problem is not any single one of them in isolation. The problem is that they all belong to the same object at the same time, confirmed by independent instruments operating across independent measurement regimes in the same observational window. And the full quantitative breakdown of what those instruments actually measured, the directional vectors of the deviations, the magnitude factors, the specific spectroscopic peaks, has not been released in any publicly accessible format by any of the agencies that collected the data.